So they tell us that the weight hanging off of it is 300 pounds. And we need to find the reactions at A and what I will call TBC, the tension in cable BC. So we start with the free body diagram of our situation here. So the first thing we have to do is choose what's the object we're isolating from its supports and from all of its other connections. So in this case, what object do we want to take apart from everything it's connected to? Right, so this T-shaped beam, pretty much everything that's blue in the picture here, we're going to disconnect it from the pin at A, cut the rope at D, and cut the rope from B to C, and that will be our object. So we're given a coordinate system here that I'm going to stick with. So I'm just going to copy down this object. I'll call it object AB. All right, so there's our T-shaped piece. So it's connected to A, which is also the origin. We're going to be concerned with point B. I'll add a point and name it G here. And we're also going to have this point C because we have that rope that's connected from B towards C. So since we're back in 3D now, all these points, I'm going to put their coordinates. They'll help us in the next steps. So B is at -4, 6, 0 feet. G is at -2, 6, 0. C is at -1, 0, 2. And A is the origin, so I'll just leave that. It's just 0, 0, 0. All right, so we have the kind of the skeleton here. We have the object and the important points illustrated. So now we have to go and start adding the forces that act on it and the couples that act on it. So I usually, just out of habit, start with the external or the applied forces. So what applied forces are acting on the beam here? Right, so that weight that's hanging off of it at G, so that's acting in the -z direction. And it'll have a value of 300 pounds. Which will be in the -k once we get to the equations. But it's in the -z direction acting at G. Right, so we have that another force. It has to be a tension, so it has to be pulling at point B. And we know that it's pointing towards point C. So that's the tension. I'll call it TBC. All right, so now the hard part is modeling our supports correctly. So in this case, we have one support at A. We have the pin connection there. So we can look at kind of that list of usually how is a pin modeled and go off that. Or again, for now, just think about in each translational direction or rotational, can it do it or can it not? So in regards to the x-axis, can we move this T-beam along the x-axis when it's connected to the pin? Right, so the pin, we're going to assume that it is rigidly fixed there, so it can't shift any. So it can't move in the x-axis, so we are going to have a force in the x-axis. I'll assume positive x, and I'll call that A sub x. In the y direction, can we pull the this beam into or out of the y direction? No. Right, it prevents it, so we have an AY. And in the z, same question. Right, so no translation is possible in any direction. So we have three components to whatever that force is, AX, AY, AZ. I'm assuming they're all positive, but you can make whatever assumption you want. But this way I know at the end, if it's negative, it just means it was the opposite of my assumption. All right, so translations are done. Now about each axis, can it rotate? So around the x-axis, can it rotate when it's connected to A? Right, so it's a pin, that's kind of the point of it. So there's no couple around the x-axis. How about the y-axis? Can we twist it this way? No. Right, prevents that. So we're going to put a moment or a couple. I'm going to do it as a rounded arrow. I'm assuming it's positive, so that means it's counterclockwise around the y-axis. I'm going to call it m sub y. Right, so if I put my thumb in the direction of y, the way my fingers curl is the positive direction it would be. Again, this is an assumption I'm making because it prevents twisting counterclockwise or clockwise, so I'll just assume it's positive. And then around the z direction, can we twist it around the z direction when it's pinned at A? Right, that's also prevented, so we'll have an mz, I will call it. Again, assuming it's positive around the z direction. Right, so we went through all 6 possible degrees of freedom there. So if we look at our free body diagram, we have 5 unknowns all at A, 3 forces and 2 moments. We have a 6th unknown, TBC, acting over here. So usually we'll have 6 unknowns in the problems. That's not always going to be true, but if for 3D, that's usually the case. So if you count it up and you have 6, probably you're in good shape. If you have 5, that's not necessarily wrong, but you just want to double check. If you have 7, there better be like a spring in there or some other way of getting more equations, because in 3D rigid bodies, we can only get 6 equilibrium equations out of them. Questions about the free body diagram. So already much more complicated than what we saw in 2D. All right, so now we can move on to, well, we'll get to the equilibrium equations in a second. We have to go back in our 3D mindset, and I recommend finding unit vectors we're going to need now. So looking at this, what unit vector are we going to need to solve this? Right, we need a unit vector that goes from B to C, because we know that we're going to have to express TBC in its component form. So right away, before I even get to the equilibrium equations, I'll get this out of the way. So we solve this, we'll get 3/7 I minus 6/7 J plus 2/7 K. We can always come back here later if we need it, but I know I'm going to need unit vector BC, so I might as well do it now. All right, now I'm ready for equilibrium equations. Again, 6 of them we're going to get, so labeling them, numbering them is really crucial to keep track. All right, so we'll start with our friend the x direction. So what's our right-hand side here? What forces are in the x direction? Right, so all of AX. Yeah. Right, so the I component or the x component of TBC, so the 3/7, and we don't know its value, so 3/7 TBC. Right, and those are the only things in the x direction. So we have 1 equation, we have 2 unknowns so far. So I'll put it aside for the moment. And I can go to my second equation and do the same thing in the y direction. So what's my right-hand side here? Right, so the j component of TBC, all of AY is in the y direction, and that's it. So 3 unknowns, 2 equations. So finally in the z direction, okay, one more piece. Right, so the applied force, or the weight force of 300. So from our force equations, we have 4 unknowns and only 3 equations. So right now there's not much we can, numerically we can't solve anything yet. It's too many unknowns for the number of equations we have. So it's a rigid body, so we're going to get 3 more equations by taking the sum of moments around a point of our choosing. So we'll come back and add the rest of the scalar equations here. So this is where we're going to get 3 equations. We're going to take the moment, which is a vector, around some point, and it's going to be equal to the 0 vector. So again, the point we choose numerically does not matter for our answer, but by hand, A is going to be the easiest point to take the moment about, because we'll have 3 unknowns acting there, so none of the forces AX, AY, AZ will be in this equation. All right, so in variables, what's the right-hand side of this going to look like? So what contributes to the moment around point A? AY, AZ, and AX all act directly on A. So the position vector would be RAA, which would be 0. Right. So the couples or the moments do. This is where we have to be careful, and this is a common kind of omission that people make. Yeah. Right, yeah, so that will also be there. I'll take a step back. We'll get to that in a second. I'll start with the my and the mz terms, so those two couples. This is a vector equation. Everything needs a direction attached to it at this point. So it's not just my. How do we have to express it in this equation? Right, my acts around the j hat direction. I assumed it was positive, so positive my j hat. And mz will act around the k hat direction. You can't have anything at this point without a j or a k attached to it, or if it's a cross product, its outcome will have an ij or a k with it. So this is crucial to keep those directions. Right, now we're ready for the weight. So the weight force will contribute to the moment around A. So that will be RAG cross negative 300k. And then we'll also have a moment due to the tension in the cable. So that will be RAB cross TBC, vector TBC. So up here, looks easy enough. Gets a little bit more complicated in the next steps. So yeah, everything will have an IJ or a K with it once we go through all these steps. Right, so MYJ just gets carried along, MZK. Now, just like in Chapter 4, cross products we are going to express with determinants. So RAG is just going to be negative 260 feet. And this will be 0, 0, negative 300 pounds. RAB cross TBC. RAB is going to be negative 460 feet. And then how do we express this third row for TBC? Right, so these are where the components of TBC go. Sometimes in problems, we might know as a number what TBC is already. In this case, we do not. But if we knew that TBC was 300 pounds, then we could use that in this step and just put numbers in here. But unfortunately, we don't yet know it as a number, so we have to put 3/7 TBC, negative 6/7 TBC, and 2/7 TBC. Right, so we have a variable in the cross product because we don't yet know the numerical value of TBC. Right, this will be feet and this will be pounds. So we have two cross products to expand. I won't go through all those steps right now because we did that in Chapter 4. But what we're going to get is we'll expand this, get IJK components, expand this and get IJK components. We already have a J and a K here. So skip a couple steps here, group all of the like terms together. So if we do that, we're going to get negative 1800 plus 12/7 TBC, I hat. Then grouping all the J terms together, I'll get MY minus 600 from this cross product, plus 8/7 TBC, J hat. And if I group all the K's together, I get MZ plus 6/7 TBC. So again, to recap, I expanded this out. I didn't go through the steps. I expanded this out. And then everything that has an I term, I group together. A J term, I group together. And a K term, I group together. So these are where I now pull my three additional equations out of. This whole thing is equal to the 0 vector, which is 0i, 0j, 0k. So what this means is that each of these coefficients will be equal to 0 independently of the others. So equation 4, 0 is equal to this, negative 1800 plus 12/7 TBC. Equation 5, I set the second coefficient equal to 0. And equation 6, the k coefficient equal to 0. All right, so notice at this point there's no i's, j's, or k's. These are scalar equations, so direction doesn't matter. This step had i's, j's, and k's attached to it. So I'm only taking the coefficient part and setting that term equal to 0. All right, questions at this point. So we now have our 6 equilibrium equations. If we count up our number of unknowns, we have 6 unknowns. We have 6 equations, so at least we know it's a solvable system. This one by hand is not bad to solve. There will be ones that are very tough to solve by hand. So if we go to the solve step, right away we can start with equation 4, and right out of there we can get the TBC, the tension in rope TBC, is 1,050 pounds. Once we have this, now everything falls into place. We can put this now into equation 1 and get the value of AX. AX is negative 450 pounds. We can put in equation 2 and get the AY is 900 pounds. And we can put it into equation 3 and they get that AZ is 0 pounds. We can then put this result into equation 5 and 6. So putting it into equation 5, we're going to get that My is negative 600 pound-feet. And if we put it into equation 6, Mz is negative 900 pound-feet.